Good evening, everybody. Welcome to this session of NPTEL course Deep Learning. I am Subhadeep Hajra. I am a PhD student at IIT Kharagpur. Today in this session, I will discuss the vanishing and exploding gradient problem in training deep learning model, and then I will discuss some of the technique which are used to reduce the vanishing and exploding gradient problem. Okay, so let me start. Okay, so you are all familiar with back propagation, right? Okay, so let me introduce the back propagation also a little bit in case you forgot about it. So first consider a deep learning model, some model. So there is some input x, and then it's first say pass through some fully connected layer. Okay, so let us consider only a fully connected, only a feed forward network. Okay, so we are not considering CNN, convolutional neural network, in this example. Okay, then say this is again passed through some kind of non-linear layer, or say ReLU. Okay, and then it's passed through the next fully connected layer. Again it's passed through sigma. Okay, and say the output of this layer is finally used as a class space. This is the final. This is what. Okay. Now let us name the intermediate variable. Say this is S1. This is T1. Okay. And then this is S2, this is T2, and finally it is Y. Okay. Now, as you all know that during training, what we do is basically minimize this some kind of loss function. Minimize. So let me introduce the parameter also. Say suppose this fully connected layer has a parameter W1. This one has W2. This is say W3. So it's a 3-layer feed forward neural layer. So we basically minimize some kind of loss function over the parameter matrix W1, W2, W3, such that some kind of loss between this some kind of loss between this y hat I comma xi are minimized sum over all training examples, so 1 to n. Okay, so our objective is, or during the training of the deep neural network, we minimize this cost function or loss function with respect to its parameter. Okay, now so this, okay, so then how it is trained? So we basically first, so during training we need to do the signal propagation in the first forward direction and then in the backward direction. In the forward direction, we basically pass the inputs. Okay, say from x, S1 is calculated, then T1 is calculated, then S2 is calculated, then T2 is calculated, and the final output y hat is calculated. Now once we got the final output, we calculate the loss between this y hat, which is the predicted value, and this and the ground truth level, say y. Okay, we calculate the loss between these two. Okay, so it's basically check that how much the predicted output y hat is close to the original output y. Okay, now if it is very close to the original output, so it's this loss takes a very low value or takes a value close to 0, and if the distance between y hat and y is very large, then this loss takes a large value. Okay, so this is called the forward propagation, and during training, next what happens is the backward propagation or back propagation of the gradient. What is done basically during back propagation? Says from this loss we calculate the derivative of this loss with respect to, say, first y hat. We calculate the derivative. What this derivative will give us? This will give us the direction in which the output or prediction should be changed or modified so that the loss reduces. Okay, so we first calculate this derivative, and then we from this derivative we calculate the next level of derivative, the derivative with respect to the previous layer, which is basically, say, dl by dt2, okay, which is nothing but dl by dy hat and dy hat by d, oh sorry, this is 2, this is, oh sorry, this is y hat, okay, and this is d2, and this is dl, this is y. So it's basically nothing but the chain rule of differentiation. Now if you see, you can, if you look carefully, then you can see that, oh sorry, that this part is same as this part. Okay, and so when you are calculating the gradient with respect to the variable of the or output of the previous layer, you are basically multiplying the previous gradient with some additional value. Okay, then at the next layer, what you will again calculate? You will calculate the next level derivative. So here you will calculate the derivative with respect to S2. So dl ds2, which is nothing but d. So it's basically very clumsy. So let me calculate it here. So dl ds2, which is nothing but d L sorry dt2 ds2 times d y hat dt2 multiplied by dl dy. Okay, so at the derivative of the previous layer is nothing but, so this part is this part is nothing but the derivative of dl uh, by dt, that is the derivative of the previous layer, and again you are multiplying this quantity with another quantity to get the derivative with respect to the previous layer. So in this way basically you calculate using the, so during back propagation you calculate the derivative of the one layer one by one from the last layer, starting from the last layer to the first layer. Okay, and as you goes from last layer to first layer, so you basically multiply the derivative of the upper layer or higher layer with the derivative with respect to the current layer to get the full derivative. Okay, now so this is basically, this is how you basically calculate the derivative, and once you calculated the derivative, actually all these are basically partial derivatives, so forget about that. So as you calculate the derivative, then during the training what you do is basically update your parameter like this, while true you say update all the parameters, like say w1 is equal to w1 minus some learning rate multiplied by dl dw1, then dw2 is equal to w2 minus l dl dw2, and 3 is equal to w3 minus alpha dl dw. So in this way you basically, once you calculated the derivative, you update the parameter of the model like this. Okay, so this is nothing but the simple back propagation training. So it's clear, right? Or is there any confusion? Is it clear, or is there any confusion or any question? Okay, so
Okay.
yeah, is there any question?
No, sir.
Okay, then let me come to the problem of vanishing and exploding gradient problem. Okay, so as we have seen, basically the derivative is as derivative, when you calculate the derivative using back propagation, you multiply the derivative of your current layer to get the full derivative. So for example, okay, so for example in this derivative, so in this derivative you multiply three derivative one by one to get the derivative with respect to s. Okay, now as the number of layer increases, such multiplication also increases. For example, if there is some kind of n layer deep neural network models, yes, for example, some n layer deep neural network model. This is x. Okay, say this is S1, S2, dot. Say this is Sn. So all the intermediate states are, um, um, named as S1 to Sn. Okay, then if you consider the derivative with respect to S1, it will be something like this. So d of L, the loss, with respect to d of S1 will be something like this, d of L d of L, d of Sn. Okay, so I need to basically check the direction. Okay, so what will be the direction? So either this way or other way. So let me check, say W1x times W2. Okay, so the direction will be the reverse one. So it is basically S1, then this is S2, this is S. Okay. So that is how basically you will calculate the derivative. Okay, of say with respect to S1. Now, as so as a result, as the number of layers increases, the length of such chain also increases. Then what can be the problem? So one problem is that, say suppose in some special case considers, okay, I am considering a very simple example. So suppose that the neural network consists of only fully connected layers. Say for example, this is a fully connected layer parameterized by W1, this is W2, in this way this is basically Wn. Okay, so it consists of only fully connected layers, and the, you know, the parameters of each fully connected layer is nothing but some matrix. Okay, then what this expression will reduce to, it will be equals to, say, d of L, oh sorry, something this way. So d of S2 and d of S2 by d of S1 is nothing but W1 transpose. Okay, and then this is nothing but W2 transpose. So in this way you are basically end up with multiplying the matrices. Multiplying the matrices from W1 transpose to W1 transpose. Okay, now what might problem? So suppose the values of these matrices are very less. So in that case, or less than, so it's basically, say, suppose each of Wi is nothing but, say, 0.5, 0.5. Okay, so for example, on an average, the matrices takes these kind of values. Then what will be the value of this resultant multiplied matrix? So it will be, so in that case, the final resultant matrix, this matrix will be say 0.5 to the power n 0, 0, 0.5 to the power. Now, as you know, as n increases, this 0.5 to the power n becomes close to 0. So as a result, so what the matrix you will get is basically close to 0. So all the elements of the matrices are close to 0. Okay. So as a result, what does it indicate? It indicates that if n increases, there might be some situation where your gradient matrix will be close to 0. Okay, so what is the problem if the gradient matrix is close to 0? Now remember that you are updating the parameters based on this gradient. Now if the gradients become very close to 0, some gradients become very close to 0, then the parameter will not get updated. So as a result, though the training will start at some points, because as the gradients become close to 0, the parameter will not change. As a result, your loss will never decrease. Okay, So this kind of problem is called the vanishing gradient problem, because in in this situation this is called vanishing gradient. Vanishing gradient problem. Okay. So in this problem, what is happening is basically your gradient with the increase of the depth of the neural network model, your gradient vanishes. Okay, gradient vanishes or becomes zero. As a result, the parameter will not get updated, and thus the loss will not decrease. So the model will not be trained properly. So this is called the gradient vanishing gradient problem. Another problem is called the exploding gradient problem, which is the reverse of this. So for example, in this case, instead of wi's having value 0.5, 0.5, if it is 1.5, 1.5, then what will happen? The ds1 will be 1.5 to the power n 0, 0, 1.5 to the power n. So as you know, that as increases, 1.5 to the power n can be very large. Okay, so in this scenario, what will happen is that the value of the gradient become very large. Now, what's the problem if the value of the gradient becomes large? Okay, so if you are familiar with some kind of gradient descent based optimization problem, you know that basically if the value of the gradients become very large, that's the model becomes very difficult to train. For example, the reason is something like this. Say, suppose you have say a loss function something like this. So now if the gradients become very high, in that case, for some moderate value of the learning rate, what might happen is that the loss might jump from say from this place to this place, then this place, then this place, then this place, like this. So instead of loss getting decreased, the loss might increase with the training iteration. Okay, so what might happen is that basically, so suppose you start from this place, in the next place you will jump to this place where the loss is more than the previous one. Okay, and then in the next step you might jump to this place where loss is more than the previous one. So in this way, so instead of loss getting decreased, the loss might increase with the training step. So this kind of problem is called exploding gradient problem. So exploding gradient problem. So anyways, either the vanishing gradient problem or exploding gradient problem is not very good for proper training of deep neural network. And for a very deep neural network, this kind of problem might occur. Okay, so such kind of vanishing and exploding gradient problem might occur. Okay, and this kind of problem is much more common in case of neural network, in case of recurrent neural network. But for convolutional neural network, also this kind of problem appears. Then what is the solution of such vanishing and exploding gradient problem? Okay, so there are several solutions. It's not solution, but so in okay, so what are the ways in which you can reduce this problem, these kind of problem, vanishing and exploding gradient problem. So here are the some common technique which is very useful to reduce such problem. One is basically proper activation function. Activation. So we will basically discuss those. So we will see that for some activation function, the vanishing and gradient. So if you use some activation function in your deep neural network, the vanishing and exploding gradient problem increases. Okay, but for some it is much less. Okay, then there is proper initialization. Proper initialization. So initialization of deep neural network parameter. Initial of the parameters of the deep neural network plays a very important role in tackling such problem, vanishing and exploding gradient problem. In fact, we will see that if the parameters are not properly initialized, there will be such problem. But if it is properly initialized, then such problem is much less. Okay. Then there are batch normalization. Certainly, batch normalization helps a lot in tackling such problem. And then residual condition. That is some kind of ResNet model. Okay. So we'll see that how residual connection helps in tackling such problem, and why, or in other words, why ResNet model is so good or can be trained even if the depth of the neural network is very large. Okay, so let us discuss those one by one. Okay. The first is proper activation. Okay, so let us first discuss the different activation function one by one, and see what is their advantage and disadvantage, and for which activation function such vanishing and exploding gradient problem is more than the other. Okay, so first let me So, can you name some of the activation function which you are familiar with? Name some activation function. Any activation function you are familiar with? Okay, so let me. Okay. So first I'll start with sigmoid. What is this? So this activation function is nothing but this one. So it uses a sigmoid function to add non-linearity to a deep neural network. Okay. So if you plot this curve, it will be something like this. Say this is -1, this is +1. Okay. Yeah. So something. This is. It will be something like this. So it it's takes a real value. So this is x, this is x, and this is sigma. Takes a real value x, okay, and outputs a value between 0 to 1. Outputs a value between 0 to 1, okay, and it takes a shape like this, okay. Okay, now what is the advantage? So the sigmoid activation has a very nice interpretation in terms of the probability. Since it takes a value between 0 and 1, you can represent a probability using this sigmoid value, okay. So as a result, so sigmoid was very popular as a activation function, and it also introduces non-linearity. But the problem with sigmoid function is that, okay, so we'll see that. So what are the problem with sigmoid activation function? So one of the problem with sigmoid activation function is that it saturates. What does it mean? So for say suppose if your input lies in this region, it has some non-zero gradient. However, as the input go beyond this region, it has almost close to zero input. It says very close to zero gradient. So as a result, what happens is that so suppose if you use this sigmoid activation function in a deep neural network, what might happen is that the gradient might get killed. For example, so you are passing the gradient one by one like this, one layer after another layer, you are passing say gradient. Now in between, in some sigmoid layer, it might happen is that some gradients become zero, almost close to zero. As a result, when you this gradient close to zero gradient multiplied with the some non-zero gradients of the previous layers, so the whole resultant gradient might become zero. So as a result, what might happen is that there might be some vanishing gradient. Okay. Now there are later improvement of sigmoid activation function, which is called tan H function. This is something like this. Tan application. Where say t of x is nothing but e to the power x minus e to the minus x plus e to the power minus. Okay, now if you plot this, it will be something like this. So now your output is bounded between plus 1 and minus 1. So earlier in case of sigmoid, the output was bounded between 0 and minus 1. Here in case of tan H, the output is bounded between minus 1 and plus 1. Okay, but here also there exists some saturating region. That means if your input lies within this range, it has non-zero gradient, but beyond that it has gradient almost close to zero. That means that it's also prone to vanishing gradient problem. Okay. However, in many situations, the tan H is a better option than sigmoid, because in case of sigmoid output, the output is always positive, which causes some kind of problem, or which basically leads to slow convergence of the deep neural networks training. However, since tan H has a symmetric output, which means it's between minus 1 to plus 1, then so tan H performs better than sigma. Okay. So, okay, then I will come to the ReLU. ReLU activation. ReLU activation. So you are already familiar with ReLU application function, which is nothing but simple function maps of 0, comma 1 minus x. Now if you plot this ReLU, it will be x. So it will be something like this. So this is 0. It will be okay. Now, so why ReLU is better than sigmoid or tanh? So one favorable point for ReLU is that it has less saturating region. That means that if x is positive, gradient is always non-zero. If x is positive, gradient is always positive. Okay, so as a result, so it is less prone to vanishing and exploding vanishing gradient problem. Okay, whereas sigmoid and tanh is much more prone to vanishing gradient problem. Okay, that is one advantage, and second advantage is this ReLU is simpler to implement, because in case of sigmoid or tanh you need to calculate the exponential function, which is costly, but in case of ReLU it's very simple function. It's a max of 0, comma x. Okay, so it's much more efficient to implement. Okay, so ReLU still has some kind of saturating gradient, some kind of problem, that is when x is negative, the gradient is 0. So it still has some kind of saturating gradient problem. So there is then some other version of, or some modified version of ReLU, like leaky ReLU. Which is nothing but, so it's basically some fx is equal to max of say 0.1x, comma x. If you plot it, it will be something like this. So this is 0, so it will be something like this. Now here you can see in case of leaky ReLU, so there is, so gradient is always non-zero. So for in the negative part also there is a small slope in the curve. So as a result, it has some non-zero gradient for negative region of x also. Okay, and there are some finer version, but so liquid ReLU has one problem, is that it has the gradient does not exist at origin. So in 0, the gradient is undefined because of this surface. Okay, so there are other version like LU or exponential linear unit.
So what about the implementation of this function, leaky?
So it's also very easy to implement.
Because it's coming into the negative side, no? Whether implementation compared to ReLU, whether it is easy or
so implementation cost is almost same for both, because it's nothing but max operation. So you have to implement just max operation. You have to perform just max operation. So it's the implementation cost wise, it's almost equivalent. But leaky ReLU has one additional advantage, is that not addition, one or rather more than one, is that it has non-zero gradient even for negative x, whereas the ReLU has only 0 gradient. Okay, so in case of leaky ReLU, gradient does not get tilt, but in case of ReLU, the gradient gets tilt in the negative point. Okay, and leaky ReLU has another advantage, is that in case of ReLU, the output is lies between 0 to plus infinity. As a result, the it's unbalanced basically. Output is unbalanced because it's only output some positive value. But in case of leaky ReLU, it's much more balanced because output can be negative and positive. So as a result, on an average, the output is much closer to 0 compared to ReLU. Okay, and there are others called LU or exponential linear unit. Exponential linear unit. Okay, so it is basically similar to ReLU, except that it is now differentiable everywhere. Something like this. It is something like this. So it's smooth. It's a smooth car and differentiable everywhere. And it has also advantage of having much more balanced output compared to ReLU. Okay, and there are lots of other variants. I can share you one blog post which you can follow or which you can refer if you want to know more about this activity, different kind of activity. So this one. How to select this? No, select it. I'm sharing it in your chat box. So if you follow this blog, then you will get to know or get familiar with some more activation function which are much more recent and can be better than ReLU or leaky ReLU. Okay, so this is the, and as you know that as you already know that this selects this activation function plays a very important role in vanishing gradient problem. So activation function like sigmoid or tannage has very or severely prone to this kind of vanishing gradient problem, whereas the problem is much less severe in case of ReLU or leaky ReLU or ReLU. Okay. So far, so these are the different activation functions. Okay, then let us discuss with the parameter initialization. Okay, so we have basically, so earlier I mentioned that initialization of the parameters or proper initialization of the parameters plays a very crucial role in dealing with vanishing and exploding gradient problem. So let us see how. So okay, now again for simplicity consider a very simple network with only fully connected network. Okay, for the time being just assume that in the network there is only fully connected layers and there is no activation functions also. Okay, so in that way we will basically able to understand the problem separately with the activation. So it is passing like this to n layers and this is the final output. Okay, final output. So y hat, this is the matrix of this layer is say W1, W2, is the value of y, and this is x. Okay, now y hat can be written like this: y hat is equal to yn y multiplied by yn minus wn multiplied by wn minus 1 dot 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 w2 w1 x. So it's basically the final output y hat is nothing but multiplication of the n matrices and then the input x. Okay. Now what will happen if say these wi's are, so this say wi's are something approximately say 0.05 point okay, then the row of wy hat will be close to 0.05 to the power n 0 0.05 to the power n multiplied by x. Okay, which is basically nothing but close to 0, because 0.05 to the power n as n increases will be close to 0, and if so the whole matrix will take a value close to 0, and when you multiply a 0 matrix with some input vector, then the output will be close to 0. Okay, so what will happen is that so this is one problem, and if you consider the gradient, as well, so your gradient will be something like this. Gradient, so d of L given by say d of W1 will be nothing but W1 transpose W2 transpose Wn transpose d of L divided d of y hat. Okay, so something like this. So okay, so if you consider this kind of gradient, so it will nothing but the multiplication of the individual matrix transpose multiplied by your gradient with respect to the final output. Okay, now again you can take the same examples. That's wi is wi's are close to say 0.5. Okay, so say wi's are close to 0.5. As a result, your gradient will be this gradient will be say 0.5 to the power n minus 1 0 0.5 to the power n minus 1 multiplied by dl dy. Okay, so again, if n is large, then this 0.5 to the power n minus 1 will take a very large value. As a result, what will happen is that this matrix will be close to a zero matrix, and you multiply, if you multiply a zero matrix with, you multiply some gradient with some zero matrix, you will get close to zero gradient. So as a result, as you can see that if the matrices are initialized to a very low value, then what will happen is your output will be close to zero, or the gradient you will generate, that will be close to zero. So as a result, what might happen is that if you use such kind of initialization to train your model, then your training might take too much time, because it will get too prone to vanishing gradient problem. On the other hand, if these wi's are initialized such that this value, it is basically this value 0.5s are greater than 1, say 1.5. In that case, what will happen is basically this value might explode. Okay, so in that case, basically the output or the gradient will explode. As a result, it will lead to some unstable training problem. Okay, so the main point is that if the weights are not initialized properly, you again can end up with vanishing or exploding gradient problem. Okay, then what is the solution, or how to properly initialize the gradient? So when some matrix is initialized, okay, so there are, the point you need to consider is that, so suppose this is a network, so this is a network, then what you need to basically consider that the mean and variance or distribution of each of these states remains almost constant. Okay, so we need to basically ensure that during the forward propagation, the distribution of the features or intermediate states does not changes too much. So it's basically S1 remains almost same. S2 remains same. S. So their expectation remains almost same. Similarly, their variance should also remain same. So you have to basically ensure that they are initialized such that okay, now using some assumption and some simple mathematics, you can show that if at some layer, say this is Wi, its input layer is say Sn minus 1 and output layer is I, and if say Wi is a n1 time or nl minus 1 times nl matrix, then if you initialize this matrix Wi using some uniform random uniform random in the range minus 1 by square root of nl minus 1 nl minus 1. So in this range, if you initialize the matrix by generating some random numbers from the uniform distribution of this range, then it can be shown that these two conditions can be satisfied. Okay, or in case of ReLU network, so such condition is basically modified to something like this, to the power n l minus 1, something like this. Okay, in case of ReLU, something like that. Okay, and if you impose some additional constraint, like so in this case basically you are imposing that as the signal propagates during the forward pass, its mean and variance remains same. Similarly, you can pose additional constraint, like say suppose this. Suppose this is say DL DSN, this is DL DSN minus 1. What happens? You might want to impose additional constraint, like expectation of DL DS1 it's not DL, DS2 will be almost equals to expectation of DS3 DS2. So if you put impose additional constant, and their variance should also be same. So if you impose some additional constraint, you will get some other bound, something like this. So your Wi should be generated from uniform in the range say 3y square root of 3 or 6, something like that. In case of ReLU, I think it's 6, and without ReLU, it's basically plus. Okay, so you will get basically so you will get such kind of initial, right? If you impose this kind of constraint, that your distribution of your signal remains almost same during both forward and the backward propagation, then you will basically, if you initialize in this way, then those kind of constraint can be satisfied. Okay, so that is how many. So main point is that you should know that the initialization of the parameters is very important, and when people or devise some kind of initialization parameter initialization algorithm, what kind of points they consider, or what kind of constraint they needs to consider during the devise of some kind of parameter initialization algorithm. Okay. Okay, so this is for the parameter initialization. Okay. Okay, now the third point what we were saying is that batch normalization. Batch normalization also can reduce the exploding and vanishing gradient. Okay, how is that possible? See, batch okay, so how it is? Okay, so you are all familiar with batch normalization, right? Right? You are familiar with batch normalization, right? Okay, so let me introduce batch normalization a little bit.
So you will be giving some information about this batch normalization, no?
Okay, so let me give some.
Yeah, because there is a confusion between this batch normalization, layer normalization, and all.
What normalization?
There is a confusion now, sir. Batch normalization and the layer normalization. Can you just give me a brief
Okay,
introduction?
okay, 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 so, okay. Okay, I will basically this. So let me share this one. So it's a very good introduction to different kind of initialization algorithm. Not different kind of. It's basically gives you a description of uh, of, of the different normalization algorithm. Okay, so for parameter initialization, you can follow this blog post. And for batch normalization, you can follow this blog post. It gives a very good introduction to batch normalization. Okay, so let me. Okay, so you are okay. So if you, I think you are already using machine learning a lot and already done reasonable amount of deep learning. That is, you have already trained some deep learning model using on some data set. If you are doing that, or even you are uh, if you have used some kind of classical machine learning technique like SVM or logistic regression, then also you are familiar that the data are, so the input data are normalized. It's a very common to normalize the input data. So suppose you have say input x, some training x1, x2, say xn, some training sample xn. It's very common that you normalize this. Say suppose your input x is say x1, x say d. Okay, so your input has say d features. Okay, now it's very common to normalize the each of the input values. So you divide this, you basically transform still creates creates a normalized input like this. Say x1 minus mu x makes mu x1 by sigma of x1, where mu x1 is the mean of the features x1 and sigma x1 is the mean of the feature x2. Then you do it for x2 as well. And you do it for all the features. Do it for all the features. Okay. So, do you know why we need to do such kind of normalization? Are you familiar that? So, are you familiar that such kind of normalization of the inputs are generally done? And the second fact is that do you know why it is done? Okay, so let me tell why it is done. So, batch normalization has many, such kind of normalization or feature normalization has many advantages, or sometimes it's very crucial to get a very good result. So, for example, say for some input, so input has two features, f1 and f2. Okay, input has two features. Okay, now say first feature has a range from say -5 to +5. So the range of the first feature is something like that, and the range of the second feature is say 100 to thousands. Then what will happen if you directly use such kind of features to train a machine learning? So as you can see, the say since the range of the or values of the second feature is much larger than the value of the first feature, the machine learning algorithm which will be trained on these features will give more importance to the second features and less importance to the first feature. So it will give more importance to the second features and less importance to the first feature. Okay, so this is one of the problems. And also in theoretically it has been seen that if the norm of your input is bounded by some small value like 1, then it enjoys better training, better convergence guarantees. Okay, so if that, which means that say suppose your input space is like this. Okay, now if your input data is bounded by a very small region, or very small region, something your data is say all lies within a small region. Okay, then the guarantee you will get is much better than say your data are spread across a larger region. Okay, so as a result, to make sure that the norm of the inputs or norm of the inputs lies or are bounded, sometimes we do such kind of normalization of the inputs. Okay, so they are very common. Okay, not even in deep learning, it's also very common in case of classical machine learning. Okay, now the question is that so obviously in case of deep learning you can basically, so suppose you have some deep learning model, something like this. So it's x is your input, then the S1, S2, S3, these are intermediate state obviously what you can do is basically uh, by following the standard practice you can standardize the features x input by say x tilde by doing making sure that all features have say uh, zero mean and uh, zero mean and one standard deviation. Okay, now if you consider that say see if you consider the full network, then you will see that x is the input to your first layer. Similarly, S1 is the input to a second layer. Similarly, S2 is the input to the third layer. So in this way, Sn minus 1 is your input to the last layer. So you might want to normalize this input as well, this intermediate S1, S2, S3, Sn as well. So you might want to normalize say S1 to S tilde, S2 to S tilde like this, such that the norm of this S1, S2 like this, S3 remains close to 1 and its means remains close to 0. So you might want to standardize or normalize each of the input states or each of the intermediate states of the neural network. Because you know, just think in case of classical machine learning, you have only one layer. So you normalize the input to that layer. Okay, but in case of deep learning you have many layers and there are different inputs to each of the layers. So you might want to normalize each of the intermediate states because each of the intermediate states act as an input to the following layer. Okay, so you want to make sure that this S is transformed to a feature which has a zero mean and unit standard deviation like that. Okay, so like this. Okay. However, the problem is how will you normalize it? Okay, well it's very easy. So you have basically S1. So you calculate the mean of S1 using say by taking the average of S1 over all training sample. S1 say I equal to 1. So you calculate the S1, the intermediate value S1 for all training samples. Okay, calculate it and then take the average of those. You will get the mean of the S1 and similarly you can calculate the standard deviation of S1 over all training samples. Now once you calculated the mean and standard deviation, you just transform this S1 by subtracting the mean and dividing by the standard deviation. Okay, it's quite simple. However, there is a problem. You cannot, if you do it during training, it will be very slow. Why? Because during training, remember that during training, in case of mini batch stochastic gradient descent or stochastic gradient descent, when we calculate the gradient, we don't have all the data set of the training data. Rather we have only one batch of the training data. Okay, so we cannot perform this mean subtraction and scaling by standard deviation, or we cannot calculate the mean and the standard deviation of the entire training data. Rather, what we can do, we can calculate this mean and standard deviation for only the current batch of the training data. So in case of batch normalization, what we do, we basically calculate the mean and standard deviation of the current batch of the training data and normalize that batch of the training data using this calculated mean and standard deviation. Again, when a new batch of training data comes, again we recalculate the mean and standard deviation over that batch of the training data and normalize the features again. So like that basically. So it's basically something like that. File to say so x1 to xb is the next batch of training data. Okay, then calculate the mean S1, mean S2, mean Sn for the current batch, for the current batch of data. Similarly, you calculate the standard deviation sigma S1, sigma S2, sigma Sn for the current batch of data. Okay, and then you standardize this S1 by S1 minus mu of S1 by sigma S1, similarly do it for all S. Okay, now okay, so this is the basic intuition behind doing batch normalize. Okay, now additionally something extra is done. When you normalize this, you also learn a scaling and bias parameter, something like that. You also learn a scaling and bias parameter for batch normalization. So you do something extra, but the basic concept is something like that. The idea is to make sure make sure that the intermediate features are normalized to zero mean and unit standard deviation. Okay, now since during stochastic or mini batch stochastic gradient descent you perform operation batch by batch, so you calculate or estimate the mean and the standard deviation of the intermediate features based on the currently available batches, and you normalize your data based on this estimated mean and standard deviation. So that's the main idea. Okay, and now there are many works which tries to explain that why it performs very well. So batch normalization is helpful for deep neural networks from many aspects. Okay, first of all, it faster make the convergence of the training much faster. So if you perform a batch normalization, so your training algorithm converges very fast, and it also helps you to take, or it helps you to use larger learning rate. In general, what happens is that if you use a very large learning rate, your training become very unstable. As a result, the loss cannot be reduced properly, or does not get reduced if you use a large training rate. But if you use batch normalization, you can use a larger learning rate. As a result, you can get much faster convergence of your training algorithm. And also batch normalization can lead to a better or can lead to a lower value of the final loss function. So it helps. It's very useful, and nowadays it's kind of so people always use batch numbers. Okay, something like that. It's become very common in deep network. Okay, and why it's performs so well? There are many theory behind it. So one is basically that it reduces the internal covariate. See, there are other theories like it smooths the uh, uh, training surface. That is, if so, if you plot, so it's basically so make the training surface smoother. As a result, it becomes much easier to train. Okay, so there are other theory, but so batch normalization also. Okay, so those kind of theories are there, and there are another advantage of using batch normalization is that it helps to tackle the vanishing and exploding gradient. So how? Let me explain. So just consider our sigmoid case. So in case of sigmoid activation function, if you can remember, you can see that it's the curve is something like this. Okay, so this is the point 0. Okay, now what's the problem with this sigmoid activation function? That is, the problem was the vanishing and exploding gradient. How? Because we saw that, or we know that within this range the sigmoid has significantly non-zero gradient, and out of this range it has zero gradient or close to zero gradient. For example, if x is here, it takes some value here, then the gradient is 0. As a result, the gradient vanishes or the parameter does not get updated. Now, so when you try to train a very deep neural network, what might happen is that the range of your input might get larger. For example, or very smaller. So for example, if your input features, values of your input feature lies within this range, then what will happen is that in this range, the sigmoid activation function behaves almost linearly. So it's almost line. Okay, so it's basically reduced to some kind of identity activation function, which does not have any effect. As a result, the network loses its non-linearity. On the other hand, or on the other extreme, what might happen is that the input might get spread very widely. So your input say might spread to this range to this or larger. So this. Then what will happen is that if input range become such spread, what might happen is that or it might be something like this, that input range varies so input range varies from this point to this point to this point, like that. Okay, in this range. Okay. So what will happen if input? So if input range varies from this point to this point, so in this region the gradient is almost 0. As a result, it leads to vanishing gradient. And similarly, for this case also, it leads to vanishing gradient problem, as only a small portion of the inputs has, or small fraction of the input will have non-zero gradients, and rest of the gradients will be 0. So as a result, it will lead to vanishing gradient. Okay. So now what will happen if you use if you use uh, batch normalization will ensure that your input is lies within properties. So this is your sigmoid. Okay. Now it ensures that your input range lies say somewhere here. So it is kind of some kind of balancing where you have some non-linear part of the activation function, so that some non-linearity is introduced in your model, and also you have some non-zero gradient, so that your model parameter gets updated. So it's very helpful to help this vanishing and exploding gradient. So this is basically tackling with vanishing and exploding gradient problem using batch numbers. And the last point I want to mention is that the use of residual connection or ResNet like model is also useful to deal with vanishing. Adding residual connection. ResNet model. So to explain, let us first consider a very deep neural network, okay, which has many layers, okay, one after another. Okay. Now, what happens, as we have seen, that if the number of layers increases, high happen, then there might be some vanishing and exploding gradient problem. Or what might happen is that, okay, so gradient is not properly propagated from the upper layer to the lower layer. So in this way the gradient gets propagated. Now what might happen is that if the network is very deep, then in between the gradient might get vanishes. Okay, so it becomes close to zero. As a result, what might happen is that this part of the initial part of the network parameter will not get updated. As a result, the training loss will not reduce. Okay, so it's basically such problem might cause problem due to the lack of propagation of the gradient from upper layer to the lower layer. Now, so as a result, what is seen is that as the depth of the network increases, you might get the higher training loss than the. So if the depth of the network increases, obviously that increase the number of parameters of the models. As a result, the models should become more prone to overfitting, or the models should reach the zero loss much more easily. However, what is seen in case of very deep network, that the training loss increases, or training loss after a reasonable amount of training, the final training loss increases with the depth of the neural network. Okay, and which is basically due to the lack of gradient propagation from upper layer to the lower layer due to the large depth in the network. Okay. Now, in case of residual network, what is it is done? You add some residual connection. What is that? It's basically, say, you add some shortcut connection or skip connection from, say, lower layer to a higher layer. So suppose you are here. So in generally network, so the network will pass from say information flow will be, say, something like this. But in case of residual network, what you will do, you will add some connection like this from here to here. You add some direct connection from this layer to this. Okay, something like this. So you add some extra connection from some lower layer to some, after some, by skipping some intermediate layer, you add some connection, something like this. Okay, so as a result, what happens is that the depth of the network gets reduced, because since there is a direct connection from, say, this layer to this layer, what will happen? You say, for example, in general, the gradient will pass this way. Normally the gradient will pass layer by layer, but if you add such kind of skip connection, then from this layer the gradient can pass through alternately in this direct connection. So gradient can pass through an alternate connection, and it can basically pass without involving this intermediate layer, without going through this intermediate layer. So using this shortcut connection. As a result, what might happen is that, so it's basically, it facilitates the faster propagation of gradient from the higher layer to the lower layer. And it has been seen that using such kind of shortcut connection or skip connection or residual connections, so these are called skip connection